Hello everyone and welcome to the second video of TEAM-NANO Educational Lecture Series about electronic textiles. My name is Heinrich Lanthaler, and today we are going to discuss about the applications of electronic textiles, trying to find an answer to the following question: can we make our clothes smarter? Without further ado, let me do a little recap about the last video learning point that basically are we described what are actually the electronics textiles and how we can fabricate them. In today lectures, we are going to understand the applications and, you know, more broadly, what are electronic textiles useful for. Let's start from the beginning. So after the fabrication process and the connection we made with all the electronics around, all the garments we are wearing, um, the other main issue we are facing is the testing. How we're going to test the electronic textiles we fabricate. So I reported here a very nice stretching banding machine, a very useful tool we can use to investigate the stretchability, bendability, in general, the mechanical behavior of the either electronics, but also the textiles. In order to do that, we have the device under investigation, which is which has to undergo a specific mechanical stress. In this very case, we're talking about a bending cycle. So basically, defining a bending circle, we would like to apply multiple bending deformation to the device under investigation. So in a way, we're applying a pushing pulling force to the device. This test is meant not only to determine the strength, but also the elasticity of both the electronics embedded onto the textiles, but also the textile itself, and the overall platform capability to deform properly without changing the device output. Or at least understand how the mechanical stress affect the device output. In order to do that, we perform such a test. So we clamp the device, in this very case with two crocodile clamps, and we do perform the cycling bending. As you can see here is the output of the device with a changing report in the percentage of the resistance output. As you can see in the flat condition, we have a specific level of resistance, pretty consistent, I would say. In the bend condition, in this very case, we were talking about a 3 millimeter bending radius, we achieved a consistent 7% for a reasonable amount of cycles, in this case, 1,000 cycles. The second testing we would like to perform is the thermal stress. So in a way, we have to think about the electronic textiles as, again, garments, clothes, and so on and so forth that have to withstand also not only the mechanical stresses, but also the thermal one. The idea then is to apply throughout specific tools such as hot plates and climate chamber, thermal humid stress to the device under investigation to understand the capability to withstand the thermal stress and to monitor their output as we did in this paper. So basically, as you can see, varying the temperature in temperature step from 20 degrees Celsius up to 60 degrees Celsius, the resistance output, as expected, since it's a resistor, so a device that changes its resistance response due to temperature change, its it resists, increasing the resistance while the temperatures increase, and vice versa. The final test we would like to perform is related to the washability, because of course, as you can imagine, these textile-based devices should withstand not only the mechanical and thermal stresses, but also the washability, the washing machine in a way. So the water, soap, and all the mechanical forces involved in the process, so friction, stirring, and rinsing. Of course, we would like to have the ideal device to withstand as much as it can the washing cycles without no deformation or no changing in the device output. A typical domestic washing cycle is with a temperature of 40 degrees Celsius, but it can be even um, harsher, with a spin of 1,400 RPM and a laundry liquid in a volume of 30 ml. Um, in the group of Steve Beebe, they conduct this study. So basically, they fabricate some antennas on top of towels, bathroom towels, and they were actually able to test them in a washing cycle. So they placed the washing capsule inside a washing machine. The cycle they wanted to perform is at 60 degrees Celsius, spinning at 600 RPM for 1 hour. And basically, they were able to read the devices during the washing itself, which is pretty uh, interesting and showcase basically the capability of these devices to withstand and to be readable also during the washing cycle. So finally, we can talk about applications. So where do electronic textiles find application? But to be totally fair with you, we can find electronic textiles pretty much everywhere in our everyday life. Starting from the automotive industry, of course, we can think of embed electronic textiles into our own cars, for instance, in the seat belts, in the car seats, in the steering wheel, the windscreens, and the dashboards, and so on and so forth, for a reasonable amount of functions such as sensing the temperature inside the vehicle, tune the temperature itself, show some maps or GPS position, help us to even drive. Why not in the future? So very interesting and broad kind of application in this sector. Second, not for importance, is the healthcare. As I mentioned in the previous video, it's already became a thing nowadays to develop embedded um, ECG or other health parameter monitoring system in our everyday life clothes, such as wristband, chest bands, smart goggles, smart glasses, smart sockets, trousers, t-shirts, and so on and so forth. Very interesting. Of course, fashion. I mentioned all these very nice clothes, but we do have to remember they're all part of they're all under the same umbrella. So the fashion industry, why don't we think about having some kind of LEDs embedded in our very clothes um, to be more fashion or to, I don't know, change basically the color of the same T-shirt based on the, I don't know, our mood, the environment that surrounds us, and so on. Sports, of course, another interesting way of applying smart textile is the sport related, because we would like to monitor our athletes' performance not only during matches, but also, and most importantly, during their trainings, understand if they are suffering of some diseases, how they can improve the performance. Um, and of course, another interesting topic is about energy harvesting. Can we actually harvest energy up to then store it into some kind of batteries and supply energy afterwards to some sort of embedded devices? Well, yes, of course. Um, it's going to be pretty much interesting to harvest energy, I don't know, from human body movement or from the environment. What about having photovoltaics embedded in our own t-shirts? So when the sun shine on us, we are also collecting some energy. What about robotics? So nowadays, it became an interesting topic to develop, um, robots made out of unconventional materials, more flexible, more exotic, more textile-based. Last but not least, I would like to mention these two final topics together because they might also work somehow together. So aerospace and defense, because we can think of embed in, I don't know, in the spacesuit, in the military vests, in the helmets, and all the in the space in the space shuttle, the um, cabin, all the text, the e-textile, the electronic textile we can think of in order to sense specific range of temperature, specific gases, specific um, conditions, all the others. In today's presentation, I would like to focus specifically on healthcare, presenting two real case scenarios, two applications. The first one was presented by Wang Li and others in Advanced Functional Materials in 2018. It's pretty old, I would say. And it's basically an electrochemical fabric. The idea is pretty simple. So basically, uh, those are coaxial. It's a coaxial-based structure based on a carbon nanotube coated with different active material. And basically, each single active material was sensible to different um, electrochemistry compounds, such as glucose, ions such as sodium, potassium, and calcium, and sensitive to pH. They place also a reference fiber based on silver chloride, and this is what actually we're able to achieve. So here you can see the silver chloride reference fiber, and here is the sensing fiber as mentioned. Here you can see the interference study they conducted on the glucose fabric. So basically they exposed the sensing fiber to different compounds, and actually the glucose sensing fiber showcase a sensitivity just to the glucose. So pretty selective. They tested also the flexibility of the sensing fibers under different bending and twisting conditions for multiple uh, bending and twisting cycles. And as you can see, it's pretty consistent and stable. Last but not least, they wanted to understand the reproducibility of this glucose sensing fiber, for instance. So one sample is basically related to one curve. And it was pretty consistent, I would say. After that, they started the electrochemical fabric and the real case scenario application, demonstrating the integration of this electrochemical fabric into a sweatshirt, as you can see here. They were actually able to monitor in real time the, the garment device, and they made actually a comparison between in and ex-situ data analyzed and collected with the sweat sample. The second healthcare application I would like to mention is this smart wound healing bandage presented by Irfa Ulla and others, so by the group of Steve Beebe. And the principle It's very simple. So it's a wireless powered ultraviolet radiation based disinfecting bandage, and it is to sterilize and to treat chronic wound in order to care and manage them. To do so, basically, they embedded a microcontroller with low power UV LEDs in the um, bandage, and the inductive coil is concealed in the fabric bandage and coupled with a rectifier circuit, as you can see here. As I mentioned before, they use this the TPU encapsulation method also for this very device in order to enhance its capability to withstand either bending cycle, as you can see here, but also washability. Its washability. And here is the final result applied on the leg of one of Steve Beebe's colleague. Uh, so basically, they started the biofilm formation after 6 hours of long UVC radiation. They started from initial cell concentration of around 0.2 optical density, and basically they were able to demonstrate that the UV light harms the cells um, by directly damaging their DNA and causing the cell apoptosis, reducing then in size um, the cell size from 4 micrometers down to 2 micrometers. Basically, they were able to report three main effects. So first thing first, the cell growth slowed down or stopped. The morphological changes appear on the cells, and last but not least, the biofilm formation was less efficient, resulting in a lower surface coverage, as you can see also here in the pictures reported. The final topic I would like to cover today, and actually was also part of my PhD thesis, is the sustainability, the future of smart textile. Because even though the majority of textiles which are introduced in the market are declared recyclable, the 85% of them roughly are not recycled at all, ending up in landfill or basically burned, which means that 38,000 tons per year in textiles matter are introduced in our environment, our surrounding environment, polluting our own oceans. How to do so? Well, the idea is basically to put the sustainability in the very center, in the very middle of the discussion about smart textile, and to work on sustainability on the entire fabrication chain. To do so, more practically, the idea is to work with more recyclable or biodegradable material, both on the electronics and also on the textile point of view, to have a better chemicals control involved in the process, in the entire fabrication chain. I'm speaking about electronics fabrication process, but also, again, the textiles point of view. And last but not least, the um, consumption of raw material should be reduced very much, considering the consumption of energy, consumption of water, but also the consumption of soil. More practically, how are we going to do that? Well, we can think about a pyramid. So starting from the very bottom, from the very substrate, we can think about of using green substrate or green-based substrate, natural-based substrates such as fabric made out of cotton, linen, lotus, seaweed, bamboo, and so on. The use of green metals such as magnesium, zinc, um, manganese, and iron, or mineral-based metals. The green dielectric mentioned in the previous video, the aluminum oxide, the perylene C, and silicon dioxide, but there's still more to be investigated. And last but not least, of course, the use of green semiconductors, among the others, indium gallium zinc oxide, which is pretty much interesting for its water solubility, the zinc oxide, but also the P3HT that I mentioned earlier. The idea should be that we have to start thinking from the very basic of the textile, the whole textile fabrication chain, starting from the yarn point of view, integration of sustainability and electronics, sustainable electronics into yarns, fabrics, up to everyday garments. In order to do that, we have to think about a more sustainable design, more sustainable fabrication process to take into account the sustainability in the performance analysis of the device we are going to fabricate, and last but not least, to have standardized life cycle assessment, life cycle analysis of the device we are going to fabricate. I would like to leave you with some further readings, which I find pretty interesting here in this very um, slide. You can find all the information. And yeah, I would like to thank you all for your very kind attention and see you in the next videos. Bye.